Okay, on to non-linear equations generally now. So we'll now return back to the issue of, okay, we want to find the cubic root now of 7, and we're going to find it by iterative formulation. Of course, there's a much easier way to do this. We could just compute 7 to the power of 1/3, and that will give us the correct answer, of course, but kind of misses the point and the intuitive nature of solving these problems and what happens behind the scenes in case you do run into problems more when you look at more complicated equations. So we'll start off with this very simple workhorse. 7 cubed minus 7 is equal to 0. We need an iterative formulae can be derived to utilise to find the solution to nonlinear equations. For instance, we could use x is 7 over n minus 1 x squared. So in this case we've just said x cubed is x times x squared, taken the 7 over the other side and divided by x squared, and said okay, we'll use n minus 1. Or alternatively, we could just say 7 over x squared, and then take the square root. Applying these in Python is a great example of the powerful and fast list comprehension type methodology. So from NumPy I'm going to import the square root of squrt, and then I'm setting up what's called here a lambda function or an inline function. So f of 1 is equal to lambda, which will take the parameter x, and then this is the inline function 7 over x squared. So essentially I'm setting up this iteration, and then I've said set x initially as 3, but the square brackets imply that x is now a list, or x1 is a list, and then I'm just going to append that by repeated application of this formula 10 times. And then I'm going to look at the second formula by setting off fn2 as simply the square root of 7 upon x. This is why we imported the square root function. Again, starting x2 off at 3, using a list comprehension to evaluate that 10 times. When we do this in the forthcoming workshop, hopefully you will see that the first of these diverges and the second converges. So systems of nonlinear equations. The process is easily extended to systems of nonlinear equations. So here we would have 2 equations which we want to solve. It's worth, first of all, as I said, just plotting these to see if there's an obvious solution to the problem. And sometimes just zooming in on the plot is enough, as we'll see, to get a reasonable solution to 3 decimal places, for instance. So what's been done here in the first instance, in this block of Python, is from NumPy I've imported the square root, but this time I've imported from matplot.lib, and in the sublibrary .pyplot I've imported this as PLT, a plotting routine. And I've said let x equal np linspace, so that's a linear space from 0 to 3, and I've used 101 points in that linear space. And then I've simply plotted x cubed minus 7, this, and then the other one is 7x minus 10 over this range, and I've got this plot. So obviously this is the straight line, so this must be the linear function in black, and the blue function is the cubic function, and we can see we've got 2 solutions. So those solutions could well give us an idea of where to start when we start iterating. Just to take a step back to the iterative process. The iterative process is simply twofold. what we would do is we would find xn from the first iteration. So we just say this is, if we want x, again, we've got to learn from where we were before. We know that this formula that we derived here will diverge. This one converges, so when we try and solve for these simultaneously, the thing to do is to use the one that converges, the routine that converges. So here we would take the 7 over the other side, so it becomes plus, and then divide x by divide the result by x, and then take the square root. So we're leaving the square root on this side, dividing by x, which tends to be a rule of thumb. Always keep a power on the other side and then take a root of it, because it tends just to converge quicker. And then it's a matter of just saying, right, this is the new approximation of n, and I'm going to use old approximations for both y and x. And then finally, once I've got x, I can find y from applying the 7 over x square rooted. So we've set this up here. We have a lambda. We've set x1 plus 7 over x0, and 7x minus 10 will equal y. And then I've plotted the graph here, and I've said, well, there'll be a solution about 0.5 and a solution about 2.5, I guess. And we could have put these values in here, but to get the thing to iterate, I've gone away from these solutions. I've got a solution about 2.4, which is over here, and a solution over here, 6.8, and I should then iterate to this solution. If I wanted the other one, I'd have to use say values of, I don't know, 0.25 and 0.75. I hope that makes sense. The secant method. Of course, the problem we had with the previous methods is stability. So, for instance, if we used this particular problem, we'll find that it is unstable unless it's very close to the root. And that's something that we'll look at, this idea of stability in the workshop. So such stability problems can be addressed, at least in part, using slightly more sophisticated methods such as successive bisection and the secant method. Just to clarify the successive bisection method, the successive bisection method requires the root to be bounded. So say, for instance, x0 and x1 bound the root. That is to say, we have a positive value of the function at x1 whilst a negative value at x0, so that obviously the root occurs somewhere within that boundary, between these boundaries. So the natural thing to do would just be to halve, say, to x2, and then compute again the value to see whether you're positive or negative, and since it's positive you would know the root is in this, so you'd halve it again, and so on until you reach the root to desired accuracy. The secant method is a little bit more sophisticated, but requires two initial guesses. So in x1 and x2, for instance, it then assumes that a straight line between x1 and x2 and predicts x3. It would then compute the value at the function and then make a decision. Has it gone past the root, or does it need to go further? So in this case, of course, it's gone past the root because you have a negative value for x3, and both positive values for x1 and x2, so you know that then you would use x3 and x2 as the next guess and repeat the process. The algorithm is described in the flowchart here. So we need x0 and x1, and then we would compute the value of x1, f of x, multiplied by the inverse of the slope in this particular case, and then after that we would find out what the value of xi plus 1, take that away from xi, so a new value minus our old value, and see whether that meets a predetermined convergence criteria. In Python this is easily implemented by simply applying for the function and then appending the function. So here I've put x1 and x2, so 1 and 2 as my initial guesses, and then here we've just implemented the formula verbatim, so xi and the function of xi is here, and then this is xi minus 1, and this is xi, and we've used a Python list comprehension to go from 1 to 10, as Python has a 0 index array, starts with a 0 index, so we'll apply the formula verbatim. So now to the Newton-Raphson routine. Here the gradient of the curve is used to find a better approximation to the root. So we have a nonlinear curve, and we can compute not only the value, but of course we're free to differentiate the function at this particular point. So we find the value of the point, we say this is a function of n, and we find the value at the slope of that point, and extend a line down to when it crosses the axis, and this must be the mx plus c. But of course the gradient at this point is simply function prime of xn. And then at xn plus 1, which has the same gradient as here, we substitute xn plus 1 into it, and the function must be 0. It's then a simple matter of solving for c, so from the first equation this would just jump over to become minus function prime xn times xn, and this would become minus function of function prime of xn times x of n plus 1. The quantity we wish is the n plus 1 value, which leads us to this formula. So if we divide out, you'll find that you get x to the n, so that will cancel with this to become positive, and then we get function of the n at the top, and this becomes minus down the bottom. So the Newton-Raphson procedure requires two function evaluations, the function of the actual function, of course, to define whether it's the actual value of it, and then its derivative. It only needs one approximation, not two, as in the secant method needs two initial approximation and a second approximation, whilst the Newton-Raphson procedure only needs one. For instance, for this particular one I've said it's equal to 1, and then I've just applied the formula verbatim, x to the I divided by the value of the function minus the value of the function divided by the value, and I've used the cute notation here of fi to represent its derivative. F double I would be its second derivative, f triple I its third, f4 would be fv, etc. So using the Newtonian notation, functional notation for derivatives. Again, when this is run, and we'll do this of course in the, you'll have an opportunity to do this in the workshop sessions, you'll find that this converges very, very quickly, actually quicker than the secant method, after about 3 or 4 iterations, I believe. There are other methods available, and of course what we've done is really an instructive method of looking at the secant method and the Newton-Raphson method, and they're very important as they're used extensively for the solution of finite element routines in ANSYS, for instance, when we would look at large deformations, large strains, plasticity effects, or alternatively, if you're doing the module with Dr. Dickinson on engineering simulation, looking at impact analysis and implicit dynamics, in explicit and implicit dynamics, the Newton-Raphson routine is used for whole matrices, very large matrices, to solve these problems. But there are other methods around. They're all available really neatly packaged in Python, and this is why we've moved in recent years from MATLAB and Scilab to Python, as the SciPy optimized toolbox, Python toolbox, has numerous tools at the disposal and a very, very neat method, packaging method on how to apply these. Brent's method's available, also Brent's hyperbolic interpolation. So Brent's method uses a combination of successive bisection and secant method, and a numerical equivalent to further numerical equivalents to Newton-Raphson, and works out which one's best. The Brent method, Brent's hyperbolic, uses an interpolation between the thing. We've also got Ritter's method, the Tom's algorithm, and Haley's method. Haley's method is indeed the method used initially to ensure that Haley's comet came back, for instance. It's, as I said, it is always worth plotting the functions before doing anything to try and get a decent approximation, and usually that approximation is good enough for most engineering applications as well, so don't underestimate the power of the plot. So import matplotlib.pyplot as PLT, and then you can just use that as a new command, PLT, and use all the methods within that function. So plt.plot. Here we've set up 2 lambdas, 2 inline functions, y1 and y2, and I've just plotted them over the top of each other in a single plot routine, and to find, actually we've got a solution quite near 0.5 and another solution quite near 0.2, or alternatively, if it's needed bounded, you know it's between 0.25 and 0.5, and here this solution is certainly between 2 and 3, for instance. And that's probably enough for doing any of these solutions. So the idea is from Skippy.optimize, it's affectionately known as Skippy in the trade, after the bush kangaroo, I guess, but of course that's scientific Python. So Skippy.optimize, import the Brent twerk or Brent method, and it needs to be given a function, and in this case I've used the functions above. So of course if I take one function away from the other, I must therefore have a solution to a simultaneous, because I put in y1 equal to y2, and that should give me the value of x. And then of course I can find the y value simply by import. Once that's found by the solution of both the equations, I can plug that back into either of the lambdas, either y1 or y2, to find the value of y at that particular point also. But it's the roots that we're after. So for instance, I know there's a solution quite close to 0.5. With Brent I've given it 0.2 and 0.6, that's the bounds of the limits. I can use the Brent hyperbolic one. Again, I've put the lambdas in on the fly here, notice. So lambda x, y1 minus y2 using these things that I've plotted. Again, Riddler is exactly the same, or Ridder I should say is exactly the same, and the Tom's algorithm is exactly the same. The only thing is you need to provide a k value. More about that in the but that's just the order of, I think it's the derivative, but more about that in the workshop sessions. So other codes, the Skippy.optimize has a wrapper function in the form of the root scalar function, which is important to be able to use. We call a wrapper function means that all these particular problems, the Brent, the Rider and the Toms, can all be used as part of this, using the same procedure, the same wrapper function, the same function to do it. So just as an example here, we have g of x is equal to y1 minus y2. We are saying this is y1 and y2. I've then plotted x times g of x, and I've put the grid on to be true, and I'm trying to compute where these roots are, one of these roots are. And so from Skippy.optimize, I've now just asked for the root scalar function, and I've said root, so this is the root of a scalar function. G is the function. The method this time I've put secant in, and of course in the secant I need to supply x0 and x1, so it's actually gone off in one command and done this list comprehension for me straight out the box. So just a few notes to inform you of the other codes are available. The Skippy.optimize wrapper function is of course of utmost importance. The wrapper function is root scalar, so this can be done simply by invoking from Skippy optimize import root scalar, and then we can import the method then. So we would solve for g, which is the function. In this case the function g is y1 minus y2. I've actually plotted g on this as well to show you that the solution should be around here and around here, and then you can import the method, in this case secant, and impose x0 and x1 as the initial and first guess. There are analogues across, or analogies across all the codes, ease being the obvious one, where you just, obviously it's an equation solver, so you just type in the equations. You still may have issues converging to either one or the other of the solutions, because it's very obvious from this that we have a solution here and a solution here. So for instance, if in ease we put in 2.5, obviously we put 20, I guess a better result would have been 2 for the y value. You can change the guesses in the variable information. More about that in the actual session, in the workshop session. Maxima does have a iterative solver, an algebraic system solver, as it were, and it tries to solve them algebraically in the first instance, but then will resort to a Newton-Raphson routine. That's the alg-sys command, and again relatively simple here. You simply set up the equations, write in the equations, and ask it to solve the algebraic system for x and y. And it's nice in Maxima. Again, it's very much very similar. However, you just define these as functions. So you define the first function, define the second function as x at y1 and y2 gx, just as we've done here. g of x becomes what's nice about Maxima is you so Scilab I guess is that you type in the functions as you would mathematically, I guess. So y here is a function g of x which takes this one away from this, and then you just simply ask for the solutions, remembering that fsolve will use a variation on the Newton-Raphson method. I think it uses Newton-Raphson as its default. It then falls back to the secant method if it gets problems, and then it starts to try and use successive bisection thereafter. And it has an algorithm if both the secant and the Newton-Raphson route in which to try and, from that guess, to try and find where it diverges until it finds where you get a crossover point to get a reasonable approximation, so that it's able to find the x0 and x1 for the secant method, for instance. And in MATLAB, again, relatively simple, we use the @ symbol to invoke the lambda. So it's at of x, and then we'll solve. And again, I've done this on the fly, in an analogous manner, which we did here for previously, when we invoked these other methods using the SciPy optimized routines, just to show you that's possible in MATLAB. All of these will find the roots accordingly. That's 0.441 and 2.397 to 3 decimal places. So now we're on to the main crux of this particular video lecture, which is interpolation, and we'll start with linear interpolation. This is achieved by assuming that each portion between the points can be represented as a linear function. In Python, there is a interp1d method as part of the SciPy interpolation module, which applies the linear interpolation formula, which is given here. This is quite simply, well, this is the rise over the run, and this is the changing x up until that particular point. So the way to derive that formula is simply to say, well, we've got y minus the gradient of the line is y minus yn over x to the n minus 1 over x is equal to the same gradient. So there's two ways of computing the same gradient, and then use the transpose the formula such that you've got y to find the interpolation, and this would find the value between two particular points. To invoke this in something like Python, you would find the module or import the module from the SciPy, the Skippy interpolate module, and import numpy as np, and we'll also need the matplotlib.pyplot as a plot. So the points on the numpy array are given. So this is the point 7, 2, for instance. This is the point 8, 3. This is the point 1, 5, etc. And then we've plotted the points as little O's, little points, and then we've said, well, the linear function flin is to interpolate these points given the kind linear, so to use that linear interpolation. And then finally we've set up a linear space between the minimum and the maximum point, and I've used 101 points in that particular way, and then we've so this linear interpolation now returns a function. Because of the object-orientated nature of Python, you can return a function, and that function anywhere in between the 2 points, you can compute that function. So this is just plot x f linear, and as you can see, we get a nice linear interpolation between the points. Moving on to Lagrange interpolation. The vast majority of methods available in data-driven analysis codes, such as obviously the Python, SciPy, MATLAB, and Scilab, even Maxima, use this Lagrange interpolation type methodology. Considering a linear function, we could say that y of n is equal to AO plus A1 xn, and AN plus 1 is equal to AO A1 x of n plus 1. And we could put these into an algebraic cast, such as Maxima, and then we like to solve the equations for AO and A1. The 1 just says take the first solution, the first set of solutions from that particular equation in equations 3, and then I'm substituting equations 3 back into the original interpolation function, which is AO and A1, so it will then take these solutions and resubstitute them in here, and then I've asked it to find out the sum of y1 is equal to y2 using these as the variables. Just get some help on fact sum. It's the factorized summation of the function of the expression, and you'll find that we do indeed get this interpolation pop out. So Lagrange linear interpolation, we can then show that this by expansion, we can show that the interpolation formula, the Lagrange interpolation formula, is indeed linear interpolation. So this is quite straightforward. Given the given the Lagrange interpolation function that we have just derived, we would simply multiply out these quantities. So this gets multiplied by this, and this gets multiplied by this. So we're clearing the fractions, put them all over one common denominator, and then we notice that the xn minus 1 would lead. We've then got this is positive. This xn plus 1 is, and then the x is negative, so we've just rewritten this in a slightly different manner. We then notice that functions, the ones that functions of x, or multiples of x, are yn plus 1 and yn, so this is where this expression has come from. And we've also said, well, we can do this with xn, so we have yn plus 1 and yn, and put a negative outside, and then also collected terms of yn. So we've collected terms of xn, collected terms of yn, and collected terms of just x. Thereafter, following that through, we can see that this can be put on the end. The yn value will lead, and this means that this particular what is put into the centre. It's then a matter of noting this remains the same, but we have this and this is the same function, so it can be is the same expression, so it can be factorized, and therefore clearing the fractions off, this will lead us back to the linear interpolation function. So by definition, the Lagrange interpolation function leads us directly and gives us exactly the same result as the linear interpolation function. So We'll now move up to quadratics. So we could now assume a quadratic between 3 points, say for instance, A0, A1 and A2, using this polynomial notation from earlier in this video lecture. And this time we would just set up a set of equations and solve these equations. If we then do, of course, you can try and solve these yourself, but this is showing the power of the Maxima CAS. I did try this using the SimPy as well, but I couldn't get it to plot out in such a convenient manner. So I think this is something perhaps that we could all benefit from looking at in the forthcoming sessions, the workshop sessions. That said, we'll see here that we get the expressions for linear interpolation, for quadratic interpolation, and now there's obviously 3 constants, A2, A1 and AO. We could, the Lagrange interpolation examples, let's consider the points 1, 5, 3, 2 and 3, 2 and 6, 7, using the outside points to perform linear interpolation of these points. So we could simply just use these points and plug in and play. So we'd have 1 minus x over 1 minus 6 times 7, and then we'd have 6 minus x, 6 minus 1 times 5, and this would lead us to the linear interpolation using the outside points. And of course we could do a quadratic interpolation. So this is just applying these formulas as is. Of course it can be verified very easily using either the Maxima or Python codes. In Python we need to import NumPy as usual, and then from the Skippy interpolate module we can simply import Lagrange, and from the NumPy polynomial we'll import polynomial with a capital P. A little bit complicated, but that is what it is, and that's how it's been packaged within the Python language. We simply provide the points and say that the polynomial is a Lagrange polynomial, and we therefore give it the points in the 0 and the 1 columns, and then the command to find out what these polynomial coefficients are is polynomial, this function, this object, which is a polynomial, and dot coefficients. So we'll produce a Lagrange type polynomial, and it will give us the coefficients of that polynomial, which can then be used for further processing. A little bit more straightforward for in Maxima, just load the particular module, in this case the interpol module, set up the points in a list, and then ask for the Lagrange points. Both of those should give you exactly the same answers that we used for the quadratic, because you've given it 3 points. If you give it 2 points, the outside points, both of those would return the linear interpolation. Moving up to quadratic, and this is just, up to cubic. This is a very popular method used in most CAD packages for cubic splines. It underpins cubic splines, and naturally just solves 4 equations. So it would solve y1, y2 and y3, 3 equations for, and a 4th equation, so we could generate all of the necessary constants A0, A1, A2, A3. Now the beauty of the CAS is really kicking in, because equations 5 would just solve all the equations, and then this is the result. You could try and trawl through that yourself. I don't recommend it. I'm sure you don't recommend that yourself. And then you can ask it to collect terms. If you collect, so solve the equation by collecting the terms, and finally the factorization sum will lead you to this result. And now we can hopefully see a pattern. If the y1 is used, you don't use it's x2, x minus x, x3 minus x, x4 minus x, and it's always x1 minus x2, x1 minus x3, x1 minus x4. So if we move on to 2, you'll see what in the top x2 isn't used, only x1, x3 and x4, and on the bottom you've got x2 minus 1, x2 minus 3 and x2 minus 4, and so on. So we could continue that process, and you can prove by mathematical induction the formula, and the formula says that it's yk. The multiple, so this is a multiple from n equals 1 to n, so the number of points that you have, or the number of constants within the polynomial, and while m is not equal to k, and you'll find that plugging that in will result in these particular polynomials. However, the computational method is much simpler than going through this process every time. Thankfully, these things are set up in Python and Maxima for us. Maxima will show exactly how these schemes are constructed. So it's quite nice. We have the points. In this case, we give the points 7, 2, 8, 3, 1, 5, 3, 2, and 7, 6. So we're back to our original point set. And we can set up linear interpolation in this manner. So we say linear interpolation of p dollar, and then straight afterwards we need to say the linear interpolation of x is the function we've just found. Same with Lagrange, same with cubic splines. And that can be plotted using the 2D. First and foremost, we do a plot of the discrete points. So here's the points, and this is discrete. We then want to plot function of x, which is linear, the Lagrange function of x, and the spline function of x, given these points. From x equals 1 to 8, and I've noticed there that the smallest value of x is 1 and the highest value of x is 8. I've put the x on the x label, I've put function of x, on the y label I've put x, and then in the legend I've said, well, the first one is the data, the second one is linear, the third one is Lagrange, and the final one is spline. So Maxima will do this, and you can see here now that if you was to try and compute a value in between any of the data points, they will give you very different answers. So don't expect each of the interpolation methods will give you different answers, significantly different answers, as we'll see moving forward. And of course, it can be extended. There is higher order interpolations available. Usually cubic's about as much as you need to go, but you could use a fourth order, fifth order, sixth order interpolation. But for the work that we do, I think we'll just look at linear, quadratic and cubic interpolation. In Python, we've put f quad, so for a quadratic, we use the interp1d. So what in the background it's doing all this algebra for you, or the algebra's already set up. So the way in which we can do it in Python is we do function qd, which is for the quadratic, interpolate, give it the points, it'll need the points, the x then the y, and then tell it what kind of interpolation you require quadratic, cubic, linear. I've then set up an x as I do normally, and however this time I've said what's the minimum points, what's the minimum value of x and what's the maximum value of x using the the numpy, min and max methods as part of the and 101 points. I've then plotted, this assumes that the MATLAB plot .pyplot is activated, so you've imported this of course, and we plot f against x lin, f against the quad and f against the cube, and of course the f lin we computed previously in Python. Plotting this over the top we get exactly the same results, or very similar results, and I think they would be exactly the same as the ones in Python, but a neater plot, I think. It is also possible to do this in ease, however you would need to set up both a lookup table and a parametric table in which to do it. So certainly Python is showing its power over its compatriots in this particular for interpolation. Other codes, there are these can be achieved in both MATLAB and Scilab, slightly different interpretations. So first of all, you'd set up the points now as an array, as we did before. Again, we've got a linear space from the minimum point to the maximum point. Remember that it's not a zero index now; it's an index of 1, and then set up the linear using the interp1 command in MATLAB. Present the points 1, so they're where the points are to be evaluated. The data, which are the actual points. XP is the value where you want to evaluate those at, and the type in which you need to do, which is linear. And the second one we have is spline. So in this particular example, we've just looked at linear and splines. I think they're the only available in the interp1. And that's the reason we use them, just for Maxima, for Scilab. I may be incorrect, there may be a quadratic option there, I don't think there is. However, moving forward, we have then plot the point using points as we did before, plot them using a linear function, and then plot them using the spline. MATLAB, very, very similar. We use the interp command, but this time the linear function is interp1. It just requires the points and xvp, which is the value to be interpolated, the interpolation value. There are other, so that would use a linear interpolation by default. The cubic is used is a pchirp command, and there's a maxima k a command to produce different types of splines. They can then just be plotted.